Okay, welcome back to the online lecture, and this is the 6th week, and we will study chapter 27. The title is circuits. Okay, what kind of circuits are we talking about? Of course, these are electric circuits. Okay. So let's review the last week's lecture. We learned that what electric current is, and we also learned the Ohm's law, which defines the resistance from electric current and electric potential. And we also learned the resistivity, which is similar to the resistance, but is independent of the geometries of the object. Okay. And then we also learned how to calculate work and power consumed by electric circuits. Okay. So in this lecture, we will study the concept of electromotive force, and we will also learn how to use Kirchhoff's rules or Kirchhoff's rules to calculate currents flowing in circuits with many resistors. Okay. And we will also study how to measure currents and voltages in electric circuits. And finally, we will learn the complex case of circuits with both a resistor and a capacitor together. Okay. Let me first explain what an electromotive force or EMF is. The first thing I have to tell you is that electromotive force is not a force, but it is in fact an electric potential. So the name is a little bit misleading, so please be careful. So electromotive force does not have a unit like Newton, but its unit has to be the volt, because it is an electric potential. Okay, so in order to explain what an electromotive force is, let's go back to the case of this potential energy doing the work. So in this figure, what is drawn here is the bucket of water at certain height. So when there is a tube or hose, the water will go down because of the gravitational force, and when it goes down, we learned that it will do some kind of work, right? Well, this animation doesn't work, so this wheel actually has to rotate when the water is going down. I'm sorry about that, but you can certainly understand what it is. So here, the lesson is that the potential energy, or actually the decrease in potential energy, can do the work. But the problem of this case is that you can do the work only as much as the original amount of water inside the bucket, right? So if you want to do a large amount of work, probably you need a large size of bucket, but nevertheless, you will do only the limited amount of work. And then what do you have to do if you want to continue working for a certain period of time? In fact, we have a very nice device which can help you to do that, which is called a pump. Suppose now you connect a pump so that the water can be continuously pumped back up into the bucket on the upper side, and then water will of course continue to flow down as much as as long as you keep the pump running, and then this wheel will continue to rotate. Okay, so I'm sorry, the animation still doesn't work, but you get the idea, right? Okay, and then let's try to apply the same idea to the case of work done by electric charges or electric potential. Okay, so in this figure, we have a capacitor charged with a certain amount of electric charges, Q. So, you know, the original symbol of the capacitor does not have plus and minus signs, but here it suggests that it's already charged by certain amount of electric charges. So how much charge is actually already here? Q equals CV is capacitance multiplied by the electric potential. So if this capacitor is subject to the electric potential difference V between these two plates, it will have the amount of Q equals CV. And then, in fact, here we need a switch, but let's assume that we just turned on the switch. Then what will happen to the electric charges? So electric charges will start to move because of the Coulomb force, and typically the electrons are those that are moving. So it will go through the resistor, and then finally combine with the positive charges and disappear. So when they disappear, how much electric potential will there be? Of course, there is no charge, so there will be no electric potential. Okay, and then this resistor does not necessarily mean real resistor, but it actually implies any electric machine or electric appliances. So when the charges are going through this electric appliance, it will do some kind of work. But how much work can it do? It will do the work only as much as the amount of charge originally stored in the capacitor, right? Just like the case of having a bucket full of water at a certain height in the previous slide. Okay, and then just like in the previous slide, if you can come up with certain charge pump that can continuously pump the charges up to a certain potential difference, then we will be able to do continuous work, just like when we had a pump that pumps the water up to the height, right? If you have such a device, then we call it EMF device, or in long, electromotive force device. Okay, and then what are the examples of such devices that continuously supply certain electric potential? Of course, the best example is the battery. If you buy a battery from a shop which is 1.5 volt, it will continue to run until it dies, right? And then it will continue to keep the potential difference, which is 1.5 volt. How is it different from the case of capacitor? When capacitor becomes discharged, the amount of charge will decrease, so therefore the electric potential will also decrease. But in the battery, the electric potential will be maintained throughout its lifetime. And same is true for electric generator or solar cells or fuel cells. So these are the examples of electromotive force devices, or in short, EMF devices. Okay. So in the previous slide, we discussed what an EMF device is, but we didn't really discuss the electromotive force itself. So here, let's try to define the electromotive force in a better way. Okay. So in the figure on the right side, we are showing an electric circuit including an EMF device. So here, this example shows a battery, okay? And then there is a resistor where the work will be done, okay? And then at the bottom of it, there is a three-dimensional graph which shows you how the electric potential goes up and down, okay? So as we have discussed previously, the point of having this EMF device is having a continuous flow of electric charges, right? So let's suppose you are counting the number of charges flowing at certain period of time, and then let's suppose that during the time period dt, suppose charge dq is flowing in the circuit, okay? And then during this time, the work has to be done by the EMF device to keep the charge flowing, and then let's call this small amount of work dW, okay? And then here we define the EMF of this EMF device as shown here. So we divide the amount of work done by the amount of charge flowing. So dW divided by dQ will be the EMF of this device, and we use a symbol V sub EMF, okay? And then the reason why we use V is we already said it is in fact an electric potential. And then how is it same as electric potential? Try to remember in chapter 24, how we define the electric potential difference. This is the equation we had, and it actually looked the same, right? So EMF is a kind of electric potential, and in some textbooks it will use a symbol like this calligraphy style E symbol, but the symbol actually doesn't matter. You can go either way. And okay, and then important thing you have to know is that when the current is flowing, and when current is flowing through this EMF device, the potential will actually increase, okay, by this much, which is VEMF. Okay, so in the graph on the right side, the current is flowing clockwise, and then of course inside the conducting wire, potential will not change. When it finally goes through the EMF device, it will go up by this VEMF, and then again in the wire nothing's changing. But then when the current is flowing through the resistor, it will again go down. How much it will go down? Of course it will go down by IR, or if there are many resistors, then it will go down by I multiplied by total resistance. And then in fact in this case it's going as a circle, so therefore VEMF in this case must be equal to the current multiplied by resistor in this case. Okay, so remember in the circuit, if you follow the direction of the electric current, the potential will increase by VMF inside this EMF device, but the potential will decrease when the current goes through the resistor. So in fact, finally, when you try to calculate something here, you actually have to put minus sign because it's decreasing. Okay. Okay, suppose you have now set up your EMF device in the circuit and the current starts to flow. Then what next? Then you should be able to calculate the amount of current in your circuit. Okay. And there are several rules you may find convenient in calculating the current, and some of them are given by this gentleman here, whose name is Jae-Ho. He was a German physicist, and his first rule is called the junction rule, and is also called the current law because it's directly dealing with the current. And this is in fact something we already studied. It is basically about the current coming in equal to the current coming out. So in this example here is I1 is equal to I2 plus I3. So and then by using mathematical expression, you can simply use these sigma symbols. So this is basically about charge conservation, and you can also call it maybe current conservation. It is applied to any node, which is, well, what is the node? Node is the place where many wires are connected. Okay. And his second rule is called the loop rule, and it is also called the voltage law because it directly deals with voltages or electric potential. So what it says is that the sum of the potential change along any complete loop of a circuit must be 0. So what is a complete loop? So complete loop means the case when you go around the circuit and then be able to come back to the same place. So in this example shown here, there are 3 different complete loops. The first one on the left side of the circuit, second on the right side of the circuit, and then lastly, if you go around the perimeter of the circuit, then these are examples of complete loops. So whichever you choose, this loop rule must always be satisfied. Okay, and so therefore you go around the loop and find any potential change you come across and make a summation, and then you will get 0. Okay, and during this summation, okay, the example here shows the EMF device and resistors, and then here we set up the loop to be going around like clockwise, right? All the arrows are pointing clockwise. So in that case, you will go through this EMF device from negative terminal to the positive terminal, and we learned in this case that the potential will increase by VEMF. So therefore, you have to the positive summation of the EMF potential, and then you go through the resistor by the current, and then we already learned that it has to be minus of IR. Okay, and there's actually something more to tell you, which is called the resistance rule. Okay, the resistance rule says that the change of potential across a resistor is minus IR along the direction of the current. This is something we already studied. But then it says that the potential across a resistor is actually plus IR along the opposite direction. Okay? Well, the example is shown here. Okay, so here we assume that the current is going down, and then think about the case when you go around the loop counterclockwise here. And then here you see the direction of the arrows are the same. Then, of course, in this case, the potential change across the resistor will be minus IR, okay? But then, now in a different case, let's suppose you assume the current to be going up. Then, these two arrows are pointing different directions, right? In that case, when you go around the loop, the potential change has to be plus IR. Why? Because the current going up by the amount of plus I is actually equivalent in saying that current going down by the amount of minus I. Okay, so therefore you have to do minus of minus I multiplied by R. So therefore you will get plus IR. Okay, and then whenever you use these rules, you first have to assume the direction of the current. Then you might ask, how do we know the direction of the current even before calculating it? Okay, so what I can tell you is that it doesn't really matter. Just try to assume the direction of the current for your convenience. Then if you get the positive value after the calculation, that it simply means your assumption of the direction was correct. And then if you get the negative value of the current, then it simply means that the direction must be opposite. Okay, so please remember that. We will probably see some examples in the classroom. Okay, and then there's another rule called the EMF rule. Well, this is again actually nothing new. If you go through the EMF device from the negative terminal to positive terminal, then of course potential change will be plus EMF. But it happens in some case that you may have to go through the EMF device from the positive terminal to the negative terminal. Then of course it has to be minus EMF. Okay, these are the simple rules, but something you always have to follow.